Number 11 is a question about music. Okay. Number 11 reads, what are the wavelengths of A5 and A3? Assume that sound travels at 343 meters per second through the air. Okay. First of all, well, what the heck is an A5 and an A3? Let me show you really quick in terms of the problems. Here we go. Okay. Number 11. Step 1, make a sketch. Okay. On a piano keyboard. Okay. And those of you that study music, you're at an advantage already. Okay. But this is a piano keyboard. And I don't expect you to sketch this out every time. I'm just showing you what this is. C, D, E, F. There we go. There we go. Mr. Lau is an artist, okay? In Western music, we have 12 notes in our scale, if you count the black keys, okay? And different types of music, there's different number of notes there, okay? But in A4, okay, is the 6th note up in the middle of a piano. It's the 4th A up, okay? And an A4 is special because that's what an orchestra tunes to. An A4 is 440 hertz in Western music. And I think, help me out here if you're an orchestra, but I think everyone tunes to the oboe or something like that, yeah? So if you're an oboe player, that's your consolation. Everyone's got to tune to you. No pressure there, yeah? Okay, and what does this mean when we say 444 hertz? It means that when you strike this note, okay, on a piano, how many times per second does the air shake? It shakes what? 440 times, okay? So in this case, picture doesn't really tell us that much, but I'm just trying to give you a context for what's going on, okay? The key is, in step 2, we want to list all of our what? All of our knowns and unknowns. On number 11, what are we trying to find? We are trying to find the what? The wavelengths of A5 and A3. Our knowns and unknowns is the wavelength for an A5 and an A3. Okay? And the only thing they give us is that the velocity we can assume is how much? 300 and what? 43 meters per second. Okay? Now this problem, number 11, is actually a continuation of number 10. Okay? So sure, what we have to do is we actually have to solve the frequency first. Okay? So let me help you with that. And the other thing that they tell us is the frequency of an A4 is 440 hertz. Okay? So here's where taking notes in your packet is important. But again, you might have a little trouble because we're actually going to go over music next Tuesday. Okay? So we'll put it together for you. But in music, we have what's called an octave. When you go up 8 notes, 8 white keys, skipping the black keys, you get what's called an octave. Okay? We got some musicians in here. You're in choir, orchestra, band. Are you play guitar, piano, or violin, or whatever? Okay? So an octave sounds good because you actually double the frequency. Okay? So here's a piece of information we can decode. An A5 is just double an A4. So instead of 440 hertz, what's double that, guys? It's 800 and what? 80 hertz. And what would an A3 be then? It'd just be half of that, right? What's the frequency of an A3? It'd be what? Instead of 440, it'd be what? 220 hertz, okay? And when we're back in the classroom, I got a little keyboard. I'll play you guys the notes, but it's just 1 octave apart, okay? If you play chopsticks with 2 fingers on the piano, okay? You can have someone play along with you an octave lower, and it sounds good because it's just double the frequency or half the frequency. Okay? Anyhow, what's going on now? Okay? Step 3. Okay? We're going to look in our toolbox to pick the right equation. Okay? And we actually have all the pieces of the puzzle. We want to know wavelength. We know frequency. Okay? And we know velocity. So which equation will help us, guys? The equation is going to work in our toolbox here. Okay, yeah, equation number 4, exactly. Good job. So we can use the wave speed equation. V equals lambda f, where V is for velocity. The Greek letter lambda is for wavelength, and f is for frequency there. Okay? So now in step 4, we're just going to substitute and solve. We'll do it twice. First for the A5 note, and then for the A3 note. Okay? So in this case, velocity is 343. Wavelength is what we're solving for. Let's do it for an A5 first, okay? And then what's the frequency for an A5? It's what? 880, right? So to find the wavelength for an A5, all we do is just take 343 and divide it by what? 880, okay? So go ahead and get out your calculators and punch that in. Take 343 and put it over 880 there. And tell me what you get. What does that round off to? Okay, 398 something? 3987. So 398.398 will round off to like 0.4, right?
Yeah.
Okay, units is what? Units is wavelength is measured in meters, okay? Put a box around your answer and have units there, okay? Yet we need to do it now for the A3, okay? So the wavelength for A3, we can use the equation again, is 343. But now what do we put in for the frequency? Instead of 880, we'll put in what? 220, okay? So now when you solve, you just divide both sides by 220. What do you get for the wavelength for an A3? Okay, 1.559. I'll just round it, okay? 1.56 meters. So notice, if we use common sense to do a double check at the end, the A3, which is a lower note on the piano, has a longer wavelength because it's shaking the air slower. And if you think about it, that makes sense in terms of common sense, right? Instruments that are bigger, okay, shake slower, and they generate wavelengths that are longer, okay? So like tubas, electric bass versus like a piccolo, a flute, a ukulele, okay? The size of the instrument determines its natural resonant frequency, which is then the sound it generates there, okay? And there you have it. That was number 11 in a nutshell there.